Hi, my name is Ron D'Alessandro. I'm Director of Advanced Product Development and Engineering here at Trans-Matic Manufacturing in Holland, Michigan. And the reason we're here today is to look at two process technologies, deep draw metal forming and screw machine, high volume screw machine processes. I've been at the company for over 30 years, and part of the reason we're doing this webinar is to educate our potential customers of some recent discoveries that we've made. And by recent, probably within the last 5 years or so, where we've been able to take what would normally be done as a machining process and actually make them into these types of parts by metal forming. And actually what it turns out being is more of like a hybrid technology that was kind of discovered by accident. And so this education conference is really to provide information on products that you may have that lend themselves to this process technology that we've stumbled upon. And I really shouldn't say stumbled upon, because it's been going on. It's more of an evolution, over 30 years of experience and watching this company grow and get into, new ideas and new markets and new process, technology. The evolution of what could be done now versus what was done, 20, 30 years ago is drastically different. So we're excited to share that information with you. Let's start off at a high level with available process technologies for making metal components. And there are a lot of them that an engineer or a buyer can choose from. Typically, we're talking about cold heading, and there's metal spinning, hydroforming, fine blanking, obviously machining, deep draw metal forming, progressive stamping. These are all metal form technologies that are available. For comparison's sake, we're talking of cylindrical high volume type components. They can either be machined as like a screw machine on a multi-spindle machine, or deep draw metal formed. The reason for the boxing gloves is simple. We look at these as now competing technologies. In the past, we really didn't see them as competing because there were things that only machine people can do. And now with some of the new technology we just spoke of, and things are changing a bit. There are a variety of machining processes. Again, we're talking about high volume, multi-spindle type processes. So when we're talking high volume, anywhere between 50,000 and 4 or 5 million per year. And when we look at metal forming technology, these are some of our bigger presses that we have here at Trans-Matic, straight side presses that actually do transfer deep draw work. There's a variety of machines also available in different shapes and sizes, configurations, tonnages. And we at Trans-Matic, we try to cover that wide variety of product, from anywhere from a millimeter in diameter up to probably 150 millimeters in diameter, and also up to 200 millimeters in depth. If you look at machine components, and these are just some precision machine components in general, and you compare those to some of the deep drawn components, you see some similarities. Again, they're all cylindrical in nature, and they're all pretty complicated as far as tolerances and configuration. But one of the differences you'll see with the deep draw parts are features, more features. And I think that's one thing that our customers aren't aware of that you can do in line while in the press. One of the specialties that we develop here at Trans-Matic is not just drawing a part and forming a part, it's also performing secondary operations that are actually done in line while in the press. This is not new, but the capability and how we do this has evolved to the point where it's extremely efficient, very accurate, and there are more features now with wide bed technology and servo type presses that we can do now that we weren't able to perform before. So the actual processes, we're looking at a live a screw machine operation on a multi-spindle. Each step of their process, they're either removing metal or performing some sort of a machining capability. Each spinning or turn of the dial gives you a new station to work with, and at the end, you'll get a complete finished part. Pretty efficient process. The transfer press deep draw technology that we're looking at here is a straight up and down vertical motion type operation. This is just a small segment of a larger transfer operation. We start off with coil stock. We blank a disc out of the coil, and then we transfer that flat disc into a series of draw stations. And then while in the press, we perform all those secondary operations if they're necessary. Now we're going to do a little comparison, and this is what we like to call two worlds colliding, because deep draw and machining are usually two separate, completely separate industries that serve their own markets. And again, as we said at the beginning of this conference, with what some of the recent discoveries are now, we're starting to penetrate into some of those machining capabilities that were previously only reserved for the machining process technology. But before we do that, we want to talk about the advantages and disadvantages associated with each of the items on the left. So we're going to start off with raw material content. With deep draw metal forming, it is a near net shape production process, very little scrap. And machining obviously usually takes more material, removes more material out, so there's more content that's involved. Cycle times, strokes per minute, parts per minute, goes to the deep draw process. We can run anywhere between 30 and 120 strokes a minute, whereas in the machining, the process is a little bit slower because you're removing metal. It's just a slower process in general. Not saying that you can't run, fast, but you start talking about some advanced technology in machining, and it's a little different animal than you would find on a typical, like a Davenport machine, for instance. Capital cost, we believe that it's a little less on machining, and again, it depends on what you're doing and how many parts you need. But capital for presses could be pretty expensive, especially with new technology that we've been investing in lately with servo presses. Tooling is also an advantage for machining, just not a lot of tools involved. As I said, it's a metal removal process, whereas with metal forming, you go through a series of tools. So you need punch, dies, strippers, nests, retainers, all the details associated with metal forming. Variable wall thickness typically goes to the machining capability, although one thing that you'll see is in the upcoming slides is through some recent discoveries, being able to actually form varying wall thickness in the metal forming process. And really what it is, when we get into it, it's really more of a hybrid type process between deep draw and cold heading that we've integrated. Threading would go specifically to machining if it's metal removing threads or cutting, as opposed to metal forming threads, which we can do in line on the press. And scrap, as I said earlier, a lot less scrap involved with deep draw metal forming. Tolerances would go to machining. It's just typically standard industry micron type tolerances that you can achieve in a machining process. However, we've done some things here at Trans-Matic where we're controlling IDs or ODs to maybe 10, 12 micron in some instances. So that is something that's a little different than what you would typically see out of a metal form technology. And as we talked about earlier, the multi-feature capability, thread forming, side piercing, knurling, extruding, those could all be done in line. And if you're going to scale up productions from, say, 100,000 to 1 million, it can be very easily done on metal forming. Each press, in general, we can run maybe 10 million pieces on one machine. Some we can run more depending on what it's on. But if you're scaling up to that kind of higher level of volume in the machining process, typically you're going to buy more machines. So here's an example of a machine component that our customer was machining in-house, and took a long time it takes a long time to make a part like this when you're machining. There's a lot of features, a lot of control, tight tolerances, a couple of different setups, a lot of capital. And they approached us to say, what can you guys do in metal forming? Well, we did a development slash prototype on the following page, where we were able to take copper, this is a C110 type copper, and actually use that technology I spoke of, which I would call more of a hybrid deep draw metal forming and cold heading process, where we're actually forcing material into a die cavity. In fact, in this particular case, we took thin material and pushed it into a cavity where we actually relocated by volume distribution into these die cavities to be able to make the material thicker in certain spots. And then at the end, we actually did an ironing process at the very top of the part that you can see. Very unique. The tooling lineup for that particular part, by way of simulation, shows that we started with a disc and then made it into a cup, and then through a series of draw reductions, we actually formed that material to make a part complete in the last station. Here's what the part looks like, and again, you can see, the gradual distribution and volume of metal being formed into, station by station to make the final configuration. And then that last station, before we clipped it off, you can see how we iron that wall at the very top. Case study. Let's take a look at an actual case study, and let's do a quick cost comparison. The part on the left, our customer was purchasing from a machine house. You can see the complexity of the part that was needed and why it was machined. You've got flats on the side, you got a thin wall on both ends, and then on the other end, you have the OD thread, and that thread was cut. On the inside, there was a critical diameter that needed to be held. So you can see the multiple thickness characteristics required. Our engineering team, our design engineers, or BAVE engineering group, came up with a new concept and said, well, we'll go ahead and make this as a metal form part. We'll control the OD so that we can get the threads. And then we'll emboss two features to hold the ID for that critical bore diameter. Once we came up with the general concept, we worked with our customers engineering team and actually came up with a way to make this part significantly at a significantly less cost. Let's compare those costs on this following chart. So raw material wise, we only used about 30% content of material as far as the overall cost was, whereas machining, it was 40. Our cycle times for the first part of the process was 1,700 an hour, and then 833, we did a double form thread rolling process. And machining, they were doing 75 parts an hour. So, we talk about scaling up, you can scale up much higher volume. In fact, if you look at the overall capacity out of our one machine, we can run about 6.6 million parts, whereas our competitor was only able to do 600,000 without, on one machine. Tooling costs was a lot more with the deep draw metal forming, 90,000 versus 5,000. But when you're talking about a cost savings running around $900,000, I mean, it's about a month and a half, and you can basically pay off that tool. 23% scrap versus 50% scrap in machining. Total piece cost was about a third of the cost of the machined component. Again, it was about a $900,000 cost reduction in the end. So what do we look for when we talk about converting a machine part into a drawn part? Not every part's going to be capable. Not every part is going to be convertible to metal form structure. But where do you start? We'd like to think you have to start with the volume. If you've got a part that's only 5 or 10,000 parts per year, really doesn't make sense to go through the expense of the development and the tooling that's required for deep draw. But if you got something that's 100,000 or more, depending on how much that part is and the type of material and the complexity, then that volume starts to become a reason, one element that you may want to consider as you convert these machine to deep draw parts. Part features that we talked a lot about. We did speak a lot about the varying what we call integrated secondary operations that can be performed while in line on the transfer tooling. Part tolerances. Again, if you have significant amount of very tight tolerance, micron type tolerances throughout the whole part, IDs and ODs, obviously, machining is going to be a better choice. If you have an ID that needs to be held or an OD, and you have a little bit more room on tolerance on the other side, then deep draw would be a good solution. Again, it's something that we'd have to look at, and we can help develop a part to give you more of an optimal design that meets your criteria from a product function standpoint. And the other thing is, anytime we start a project, one of the first things we ask for is a design and failure mode analysis. It's important for us to understand what's critical on the part, what are the mating components, what's the stack up allowance between the mating parts, what are the failure modes within that part, what are the severity ratings for the failure mode, so that we could actually develop a process FEMA around that product. And then that helps us and guides us in terms of how we tool the part and how we control the critical features. So with that, I wanted to thank everyone for attending this conference, and also remind you that we're here to help. And if you have a product or you have an application that you think might be a potential candidate for a metal form component, give us a call or shoot us an email. My email is r.sandro@transmatic.com. We'd love to help you. And once again, thanks again for attending the conference.